This is the rest of the notes for section 1.4 on continuity, so you should have your note packet out and we'll kind of go through it. The first part of this on this page here is pretty much, it's a lot of information visually, but actually the thought behind it is pretty common sense. So I'm going to try to just explain what this whole page is saying. There's not much to write on here. But yesterday we talked about functions that were continuous, and we talked about what had to happen for them to be continuous, and we classified them as either removable or non-removable discontinuities. And what these are doing right here is giving you some properties that are true. If you have two functions that are both continuous, and then they say b is just some number in all of these properties right here. They say if they're all continuous at x equals c, then basically you can do a constant times the function and it's still continuous. That probably doesn't make a whole lot of sense right off the bat, but basically let's just give you a basic function of, say, a parabola. We know that y equals x squared or f of x, all the parabolas are continuous at all the points in their domains. And all that's saying is, you know, you can put a 3 in front of there and it's still continuous. This one says that if you have two functions that are both continuous at c, you can add them together. So maybe I take a function that's x squared and another function that's defined as being x minus 1, and I add them together and I come up with this singular function. Notice I've just taken that and I've made basically a quadratic or a parabola, which is still continuous. And again, I'm just trying to give you kind of some examples to go with this. Likewise, they say you can multiply two continuous functions and they're still continuous, and you can divide. This is very important though. Keep in mind that we can't have that denominator equaling 0 because that's going to give us a discontinuity there. So yes, I can take x squared minus 1 and divide it by x plus 1. But because my denominator can equal 0 at negative 1, I've got a discontinuity there. And we talked yesterday about how that discontinuity, when I factor and do this analytically or with some algebra, because this cancels out, what that does is we've got a discontinuity, and we talked about how graphically then, really what I've got is the line x minus 1 with a hole in it where x is negative 1. All right, so you can, so it's called removable. We could just redefine it. So we could say at negative 1, I'm going to redefine f of negative 1 as being negative 2, and I fill the hole. We talked about that yesterday, but you do need to watch out for that denominator. That's kind of all these little details are pretty important. So going down to the bottom, because we can combine all this stuff, we can actually say on the bottom here, it says the following types of functions are continuous at every point in their domains. So basically, polynomial functions are continuous at all points in their domains. Graphically, what that means is, you know, your polynomial functions are like your line is a polynomial, y equals, say, 2x plus 1. That's continuous everywhere. Its domain is all real numbers. Your parabola is continuous everywhere, and its domain is all real numbers. Your cubics, you know, and graphically we've got our lines, we've got parabolas, we've got our cubing functions. Generally the 4th degree will cause some sort of, and 5th degree, you know, they kind of all look like that, your polynomial functions of some sort, and they're continuous everywhere. Rational functions can be written as a polynomial divided by a polynomial. These are also continuous everywhere, again, as long as that denominator does not equal 0. And again, that creates a discontinuity. It can create either an asymptote if it's non-removable, or a hole in the graph if it's removable. Our radical functions also, again, it's kind of important where it says at all points in their domains. We know that the y equals square root function, the parent function of that looks like this, right? So you can see that its domain is actually from 0 to infinity. And at every point in its domain, it's continuous. I do not have to lift my pencil. But, for example, if I were to leave the domain and say at -2, well, it's obviously discontinuous because it doesn't even exist there. So you kind of have to watch out for that. Otherwise, so these are continuous everywhere, and composing them is still continuous down here. So this is a lot of information, but it's basically just telling you what functions are continuous. And so I want to talk about a trig function here. It says discuss the continuity of the function f of x equals tangent of x. And recall, it's always helpful maybe to kind of think of that as your sine x over cosine x. It's also very helpful when you're doing trig to kind of get that visual of that unit circle in there. And what we really like to do kind of too is keep in mind all these corner points are very helpful when you're doing your trig also. So I'm going to go put these on here and you can put them in your notes. You should remember the shape of this graph from pre-calculus, but I kind of want to make sure you understand it. So we're going to go graph f of x equals tangent of x. And keep in mind, we're going to have a problem or a discontinuity when the cosine of x equals 0. That's going to cause us a problem. Now look at where that happens. The cosine value is the x, and that happens here up at pi over 2, and down here at negative pi over 2, or if you want to think of it as 3 pi over 2, where our function isn't defined there. We've got a discontinuity. Not only that, it's a non-removable discontinuity. Remember, nothing's going to cancel algebraically. Whenever we do our trig, it's always nice to label your axes by pi over 2 intervals. So we would do pi over 2, then pi, then 3 pi over 2, and then 2 pi generally to the right, and likewise to the left, we would go like this, all right? So I've already told you we've got a problem at these two spots. We've got non-removable discontinuity. It's actually infinite discontinuity. We'll put that on here. And the shape of your graph, you did this last year. I'm going to go put a 1 here and a -1 here. Let's see what happens at 0 radians over here. At 0 radians, my tangent would be the sine over the cosine. So it goes through 0, 0. We also kind of know that at pi over 4, we've got root 2 over 2, root 2 over 2. At those places, we are going to have a tangent equal to 1 because we're going to be dividing two equal values. So, excuse me, at pi over 4, right about here, we have a 1. And likewise, over here, it's going to be a -1 at negative pi. So I'm going to go this way. All these are either going to be 1 or -1. And you remember this graph from last year, so I don't want to beat it to death. But it runs that cycle as it goes around the unit circle. So when I say to discuss the continuity, it's continuous everywhere in here. And basically you would say it's continuous from negative pi over 2 to pi over 2, and then it's continuous again from pi over 2 to 3 pi over 2, and then it's continuous again, and sometimes they'll put a union in these to tell you that, excuse me, that you're pulling them together, but actually I don't think the back of your book even does that. And so you just got to block out all these, and it goes there forever that way and forever that way. So just get a good idea of that cosine graph, the tangent graph. And let's move along here. This page I'm going to wait on. Last up, the intermediate value theorem. And I'm going to have you star this. This is one of a few theorems in here that I'm going to call an existence theorem. Sometimes on your AP exam, it's going to say something like verify the existence of, and we're going to have 2 to 3 existence theorem. And the first one is called the intermediate value theorem, but we can just call it, they're okay with you calling it the IMT. This is our first existence theorem, and it's very easy to understand outside of this context. Graphically and in a real world context, you'll be going, well, duh, it totally makes sense. So what I'm going to do first is pick this theorem apart. So I would like you to go draw yourself a graph. And it says if f is continuous on a closed interval from a to b. So I'd like you to go down here and go a, and it's closed. And let's go over here and let's think about b and think of it as being a closed interval. So I can be a or b. And it says that if your f of a or your y value at a doesn't equal your y value at b. So what I'd like you to do here is let's go up here and maybe call this f of a and put a dot. And let's put f of b someplace else, maybe up here. So what I've got here is the point a, f of a, and b, f of b. And I've got a continuous function on that closed interval. So basically what that means is I'm going to connect them somehow without lifting my pencil. So maybe I'm just going to go like that. It says k is some number between f of a and f of b. I'm going to put it right here. Okay, some y value between those. What this says is there must be at least one number in this interval so that f of c equals k. So watch, I'm going to go like this and head across here. And I've got it right there. F of c, my y value of c, equals k. And that's the graphical and the book definition of it. But basically what that's saying is if you're going to be continuous and you're going to go from one to the other, you've got to hit everything between it. It's kind of like if you were growing, and if you grew from 5 feet, say 2 inches, to 5 feet, 5 inches, at some point along that growth pattern, you must have been 5 feet, 3 inches. So let's go down here. It says things to note. There might be more than one in that interval. So I'm going to go back up here and I'm going to do that really fast now. Draw my graph the same way. And if I were to draw it like this, still a continuous function, and if I were to say put my k right here, you can see that there's a c right here where I hit that y value, one right here, one right here, one right here, one right here. So there's a lot of them in there. It could be kind of like you're driving your car. And you could say, well, you went from, you started at 50 miles per hour and ended at 65. Well, that means at some point in there you were going 62. Well, you might have done it a bunch, but at some point in there, you had to hit 62 miles per hour. Second thing that's important with this is that it has to be a continuous function. And again, if it's not, it's kind of intuitive why right here, if I make a function that's not continuous, then if this is my c, and again, this is your A, this is your B, I don't like to keep drawing it. Right here, there is no c such that f of c equals k, because I gapped it out. So your function does have to be continuous. And you might be thinking, well, I'm going to extend this page. What is this used for? Basically, what we use this for the most is to verify the existence of a zero in an interval. Basically an x-intercept. So on the next page here, I'm going to move it on over. I'm going to go do just that. And I think I have time to finish this one. And I am also going to then have to do probably another 5-minute video when this one's done. So it says show that I have at least one zero between x equals 2 and x equals 1. Well, first of all, what I'm going to do is go find my f of 2, which is going to equal 8 minus 2 minus 1. It's 5. Then I'm going to go find my y value at the other endpoint. In the other picture, this would be like your f of a and your f of b. It would be 1 cubed minus 1 minus 1, which is a negative 1. And I'm supposed to explain why there's a 0 between those two. Well, it's kind of obvious. If I drop from 5 to negative 1, I must have gone through 0 at some point. So the y value must have been 0. And this is a continuous function. It's one of those polynomial functions. So you would say by the IMT, intermediate value theorem, okay, there must be a number, or let's call it a c, in the interval from 2 to 1, such that when I do